Okay, so welcome to the lectures of Power System Dynamics and Control course. So we are continuing with the representation of synchronous machines, right? So in the last class, already we did a generalized analysis how we can transform or convert from one machine reference frame to the common reference frame, that is the network reference frame, right? Already we discussed this. We can see here, this is your network reference frame, this R and I, right? R axis and I axis, and D axis and Q axis, they are representing the machine reference frame, right? And under steady state, both these reference frames are rotating at synchronous speed. Okay, because the rotor is rotating, because this D axis and Q axis, they're lying on the rotor, and because the rotor is in the synchronous speed under steady state condition, so therefore both will be in synchronous, and this delta angle delta will not change when under steady state condition. But as soon as there is some disturbance, the rotor, please mute yourself. So if the rotor happens to be slow down or accelerate, during that time your delta will change, right? Because both the reference frame will have some lagging, right? So it will vary. It will not, the angle between these both reference frame will not remain same, right? So already we have discussed this, and now we'll continue. So we found the expression, and finally we found that the terminal voltage, if we are representing in D and Q axis voltages, then it should be multiplied with j e to the power j of delta minus pi by 2 in order to refer to the RI reference frame or common reference frame, right? When we do analysis in the machine reference frame, VD plus JVQ is fine. But when we do the analysis in the network reference frame, then we need to multiply this quantity, this dq axis quantity, into e to the power j of delta minus pi by 2, right? So therefore, it is very essential. Even if it is the current quantity or voltage quantity, it doesn't matter. But we need to multiply this factor. This factor is e to the power j of delta minus pi by 2 in order to transform the dq axis quantities into the common reference quantities, right? And if we want to find the dq axis quantities in terms of the terminal voltages, if the terminal voltages we know from some load flow analysis or from mathematical analysis, then we can easily find the dq axis component Vd plus jVq just by multiplying again e to the power minus j of delta minus pi by 2, right? So then after multiplying, we'll find this equation, that is Vt sine of delta minus alpha plus j of Vt cos delta minus alpha. So this equation indicates if we know the terminal voltage and we need to find Vd and Vq, the voltage in dq axis, then we need to multiply, or we can write simple the equation Vt sine delta minus alpha plus j Vt cos delta minus alpha, right? Now we know the current will be lagging the voltage by the angle phi, right? So therefore, if the current is making an angle of gamma with reference axis, this is your reference axis, right? R axis. So then we can say that your phi will be alpha minus gamma, because alpha is the angle between Vt and the reference axis, and gamma is the angle between IT and the reference axis. So there phi will be alpha minus gamma, alpha minus gamma, right? Okay, say so that this is the conclusion what is mentioned here. Whenever the starter voltage and current expressed in dq axis and needs to be transformed to the, because whatever analysis we'll do in the multi-machine system, it has to be referred to a common reference frame. Okay, so therefore each of the Mason quantities has to be transformed or converted to the common reference frame by multiplying e to the power j of delta minus pi by 2. Okay, so where delta, we know delta is the load angle and it is the angle between q axis of the individual generator with respect to the common reference frame. It is not the angle between the q axis and the Vt term. Previously, in case of single Mason case, we consider delta is the angle between q axis and the terminal voltage, because at that case, uh, under that case, we considered Vt as the reference voltage. But here we are considering the r-axis as the reference voltage, which where the r-axis is the real axis of the common reference frame, right? Okay, so here the delta is the angle between the q-axis of the individual generator with respect to the common reference frame r-axis. Okay. So this is what we have already studied, and let us try this analysis with a single Mason infinite bus system where the single Mason is connected to an infinite bus through a transmission line, and the transmission line impedance is given here, RT plus JXT, right? And it will consider the infinite, the voltage of the infinite bus as the reference. So where we'll put the common reference, okay? Common reference frame of common reference, right? Okay, so this is your single Mason infinite bus system where this is your infinite bus. That means grid. It is, we can say the grid bus, right? Where the Mason is connected, right? Now here up to this is your all Mason quantities, and this is your terminal of the generator, right? Vt to the power j alpha in the common reference frame. And xt, rt, they are the transmission line parameters. Rt is the resistance, xt is the reactance. Now from here, the generator will inject the power, that is P plus jq, right? And the current, if in terms of id and iq, I'll write id plus jiq e to the power j of delta minus pi by 2. It is in the common reference frame, and similarly this is equal to, this is nothing but equal to IT, terminal current, e to the power j of gamma, right? And here the terminal voltage similarly in terms of dq axis parameter and common reference parameter is represented here. And we know the internal voltage of the generator is EQ. So in order to transform, or in order to convert this into the common reference frame, I need to multiply e to the power j delta minus pi by 2. So therefore EQ into e to the power j delta minus pi by 2, right? So this is your terminal voltage obviously, and IT is e to the power j gamma, right? Already I mentioned a phi equal to alpha minus gamma, right? Now let the generator supply a complex power, that is P plus jq to the infinite bus. Then I can write the current expression in terms of power. I can find the current in terms of power, that is P minus jq by Vt to the power minus j alpha, because I know that Vt it star is equal to P plus jq. So therefore your Vt star it will be equal to P minus jq, right? So therefore from this expression I can write it is equal to P minus jq by Vt conjugate, that is in fact represented as Vt e to the power minus j alpha. This is Vt conjugate, right? Okay. So now if you'll write the equation for the internal voltage, how I can write? I can write it in terms of terminal voltage plus current into the parameters, the network parameters, right? So now I can write, this is given, terminal voltage is your Vd plus jVq e to the power j delta minus pi by 2 plus The parameters, the generator synchronous machine parameters are Rs plus J xq, which will be multiplied with the terminal current, that is Id plus J iq e to the power J delta minus pi by 2, right? So this is nothing but equal to Vt e to the power J alpha plus, just in the terminal quantities if I'll write, this expression will look like this. So now if I'll just multiply e to the power minus j of delta minus pi by 2 both side, I will get EQ, right? The EQ will be equal to, it is nothing but it is equal to JAQ, right? Because it is in the DQ axis, it is lying with the Q axis, so therefore it is JEQ, that is equal to J, it is equal to, obviously you know, JXMD IFD minus XD minus IQ into ID, right? So if I'll substitute this quantity here in terms of EQ, right, JEQ, then what will happen here? If I'll substitute, it will become JEQ e to the power J delta minus pi by 2. So this is nothing but equal to, I can write, if I'll write it in the terms of magnitude and e to the power in the angular form, then I can write it as EQ e to the power J pi by 2, right? So JEQ nothing but is equal to EQ into e to the power J pi by 2. So just multiplying this, I will get EQ into e to the power J delta, right? So that will give me equal to Vt e to the power J alpha plus Rs plus J xq it e to the power J gamma. So it is clearly, we can see that this EQ is having an angle of delta with reference to the Ri axis or the reference axis, right? so now from this calculation of the terminal internal voltage, it is clear, even if we are doing the analysis considering the reference frame, common reference frame, that shows that EQ internal voltage is making an angle of delta with respect to the reference axis, right? So here is your phasor diagram, right? So this is your Ri axis. You can see here, this is R axis, this is I axis, and V infinite is here, right? V infinite means the voltage of the infinite bus voltage, right? This V infinite, because it has angle of 0 degree, so therefore it is lying in reference to the R axis, right? So this is the reference voltage, in fact, right? So now your Vt will make an angle of alpha with respect to R axis, and It will make an angle of gamma, and your EQ, internal voltage, will make an angle of delta with respect to the R axis, right? And then if I'll add the RSIT and JXQIT with Vt, I'll get EQ. Obviously, we have seen in the equation. So we found EQ, which is lying in the Q axis. And this part we know, because we know EQ is nothing but J of XMD IFD minus XD minus XQ ID, right? So therefore, if I'll add this term with EQ, that will give me XMD IFD. So XMD IFD is up to this point, okay? So this is the phasor diagram, simple phasor diagram, right? So then the network equation. Now I'll write the network equation, that is the relation between the terminal voltage and the terminal voltage starter current and the infinite bus voltage. Because whatever relationship we have seen till now it is the relationship between the internal voltage and the terminal voltage. Now we'll see the relationship between the terminal voltage and the infinite bus voltage, okay? So this is the equation, this is the terminal voltage, which can be written as V infinite plus infinite bus voltage plus the transmission line parameters into the current injected, right? So the current injected is obviously ID plus JIQ e to the, so in the common reference frame, the dq axis parameter is multiplied with j delta minus pi by 2. So by doing that, we found the terminal voltage, and in terms of dq axis parameter, we will write it will be v infinite e to the power minus j of delta minus pi by 2 plus RT plus jxt into id plus jiq, right? So now this equation, if I'll write in terms of matrix form, in the matrix form, this equation, Vd and Vq, if I'll segregate real and reactive part, then Vd will be obviously RT, Id, right? Minus xt iq plus V infinite sine delta. Okay. Similarly, if we'll consider the imaginary part, your Vq will become xtid plus rtiq plus V infinite cos delta. So in the matrix form, I can represent this terminal voltage in the dq axis parameter, right? Now, if we'll write the power equation, complex power equation in terms of dq axis parameters, then how I'll represent. So I know the complex power is P plus jq, that is equal to Vt to the power j alpha into It to the power j gamma conjugate, right? Just substituting the dq axis parameters here and multiplying it and segregating the real and reactive terms, I'll find VDID plus VQIQ plus J of VQID minus VDIQ, right? So this is how, if we know the DQ axis parameters, VDID, VDVQ, IDIQ, you can directly compute the complex power. Okay, just using this formula, right? Similarly, we can find the electromagnetic torque equation as well. So the electromagnetic torque equation also looks like this. Okay. Already you know this equation, this ID IQ minus IQ ID. So now we'll see the multi-Mason representation. How we'll represent the multi-Mason along with the network during our analysis, right? So in previous slide we did single Mason infinite bus. There we considered infinite bus as the reference voltage, which is lying along the R axis of the common reference frame, right? And here in the multi-Mason system, your reference, your slack bus voltage will lie in the reference R axis of the common reference frame. And each of the Mason, the Q axis of each of the Mason will make an angle of delta. So this delta may not be equal, it will different for each of the Mason. So delta 1, delta 2, delta, whatever, if you have n number of Masons, it will be varying, right? So in a power system, there will be multiple synchronous Masons with their respective exciters, turbines, speed governors, and load distributed throughout the system. Okay. So all these components we have in the system. So the synchronous machines and loads are connected through the power system network and is through the transformers and transmission line. So for a total system representation, the system network model also should be included along with the synchronous machine. So along with the synchronous machine, exciter, turbine, speed governor, and load model, we have to also consider the network model right here. So in order to represent the whole system. So now let us consider that there are n number of buses in a system. Let us consider a system having n number of buses, and out of which m represents the number of load buses. Okay, and ng number of generators are there, or generator buses are there, you can say, right? Hence ng number of generators are there, right? So that dynamics of the ith generator, if we'll consider, along with the exciter, steam turbine, governor, then how it will look like, all the dynamic model we know, right, for a generator. So the model for each of the generator can be represented in a general form considering the ith generator. So like we represent in case of load flow, right? So this dynamic model can be represented in a general form, that is for ith generator. Let us say this is for ith generator, and that is valid for all the synchronous machine, right? So this is what we know this equation already. So these are all the differential equations associated with the stator, and this is your swing equation, already we know, and these are the exciter equations, okay, and these are your turbine equations, dynamic equations, and this is your governor dynamic equation. So all equations are written for the ith generator. Therefore, we can see a subscript I is mentioned here. For each of the parameter, we have mentioned I, right? Because it represents that this is the parameter associated with the ith generator, right? And then stator algebraic equation is here, right? This is equal to psi d and this is equal to psi q, right? So already we know this. So now here, so I equal to 1 to ng, that is because these equations are only valid for generators. So therefore we can say that I belongs to 1 to ng, okay? So these ng generators are connected to the network, and in a power system network with n number of buses, the injected current at all n buses can be written in terms of admittance matrix. Already you know this perhaps in during the load flow study. We can write the injected current II at a particular bus. How we can write it? In terms of admittance matrix, right? I can write it as Yij Vj, right? Summation of j equal to 1 to n. So this already you know. The bus voltage. So the current injected at ith bus is given where I equal to 1 to n for all buses, this form, right? This is what is mentioned here. II is equal to summation of Yij e to the power j alpha ij Vj e to the power j theta j. So j is from 1 to n, right? So here alpha ij is different than the alpha we have considered for the terminal voltage. We have considered this 1 alpha for terminal voltage. Here we will not consider alpha for multi-machine analysis. We are not considering alpha as the angle of the terminal voltage. We will consider here the theta, because these are the terminal voltage, theta as the terminal voltage for the machine, right? The theta is the terminal voltage angle for each of the machines or each bus, right? Okay, generally we consider in terms of theta. So then we are considering here the angle of the Y bus matrix element is alpha ij. Okay, because Y bus elements generally represented ij in terms of I and j. So therefore this is the element ijth element of Y bus matrix, Yij. And this is a complex quantity. It has a magnitude and an angle, right? So this magnitude is represented by Yij and the angle is represented as alpha ij. Okay, I hope it is clear. So now if I'll write the power injection equation, that is Pi plus jqi, then I can write it as Vi into Ii star, right? So Vi is nothing but Vi magnitude. This is Vi Ii star, right? Vector quantity. It is complex quantity. So this complex quantity I can write Vi magnitude e to the power j theta I. And similarly Ii is a complex quantity, the conjugate of that. So I can write it in terms of this, in terms of admittance matrix and voltage, right? So then just substituting this here in this equation, I can get this. Vi Vj Yij e to the power j of theta will remain as it is because we have taken conjugate, so therefore it will become minus j theta j, okay, and minus j alpha ij. So therefore it is mentioned j of theta I minus theta j minus alpha ij, right? So this is simple equation. Now I can segregate both real and reactive power injection. So your real power injection Pi is nothing but equal to Pgi minus Pdi. So that is equal to, I can write if I'll segregate, consider the real part only, then it will become Bi Vj Yij cos of theta I minus theta j minus alpha ij, right? Similarly, I can write the reactive power injection equation, which is nothing but equal to Qgi minus Qdi. Perhaps you know this, how the power injection is written here as Pgi minus Pdi and Qgi minus Qdi, because in a bus, if we'll see, just I am little bit for your information. Many people you know this, but for your information, I'm okay. Here it is a bus which is connected with one generator, and this is the transmission line which is connected to other buses, and here we have a load, right? So let us say this load is PDI plus JQDI, and the generator here generating is power is PGI plus JQGI. Now, if I'll write the injected power to the network, that is Pi plus JQI, this is the injected power. This will be nothing but Pi plus JQI is nothing but equal to PGI plus UGI minus PDI plus JQDI, right? So just Kirchhoff's current law we can apply here, and that will give us the power injected into the network at a particular bus. Okay, so therefore it is mentioned Pi is equal to Pgi minus Pdi and Qi equal to Qgi minus Qdi, and that is equal to the real part of this. Okay, and this is the imaginary part of this. Okay, so then okay, now if we'll write this Pgi in terms of dq axis parameter, already we derived earlier, right? Terminal voltage and the current injected to the network. So PGI will be real part of this, right? Vi to the power j theta I, and in terms of dq axis parameter, because in the generator the current we know in this form only, right? dq axis form. So therefore we need to multiply the transformation constant, or we can say the transformation parameter, to the common reference frame, that is e to the power j delta I minus pi by 2. Okay, so already we derived this equation earlier in the previous slide. Just writing the PGI equation, it is IDI VI sine of delta I minus theta I plus IQI VI cos of delta I minus theta I, right? Now your QGI become similarly, it will become imaginary part of the terminal voltage and your terminal voltage and your terminal current, right? That is in terms of ID and D and Q axis parameter. So that will give me IDI VI cos delta I minus theta I minus IQI VI sin delta I minus theta I, right? So now I can substitute in terms of PGI and QGI these quantities, whatever we have derived for PGI and QGI, right? So now I substituted this in terms of PGI in this equation, and again QGI here in this equation, right? After substituting, we find this equation, that is just substituting, I'll find this equation, right? So this is called the power injection equation, right? So this is equal to Pi, this is equal to Qi, and this is valid for all the generators, or we can say all the generator buses. Okay, not other buses, other load buses, because at the load bus there is no generator, so therefore these quantities will become 0, right? So you can see here this is valid for I equal to 1 to ng. That is only it is valid for the generator buses, right? Okay. So now we can see this is, in fact, this equation is valid for the load buses only, right? So this is PDI VI, that is because the generator power injection, real power generator injection will be 0 and at the load buses. So PG will become 0 and QGI also become 0 here. So therefore we can write the power injection equation in this form. So this is valid for I equal to NG plus 1 to N, because the rest of buses are the load buses except the so when we'll write the equation for the generator buses is 1 to NG, then the other remaining buses are all load buses. So that is from I equal to NG plus 1 to N. Okay. So now I'll consider a special case of impedance load. Okay. So just considering the impedance load, we'll see how our network equation we can write. So impedance load means if the loads are represented as constant impedance, then your differential algebraic equations can be simplified to a significant extent. Suppose the load at ith bus is represented by an impedance load, let us say, then the real and reactive power drawn by the load can be given as this. Okay. So this PLI, this is the load at load bus, at a particular load bus, ith load bus. So I can write PLI plus JQLI is nothing but VI square by ZLI. It is not ZLI, it is ZLI conjugate in fact. Okay. So how it is come? In fact, we know PLI plus JQLI is nothing but it is equal to the voltage at that bus, ith bus, into the current drawn by the load, let us say ILI conjugate, right? So that will give me VI into ILI is nothing but I can write VI because the voltage at that particular bus, VI by, because it is a constant impedance load, so therefore I can write like this, VI by ZLI conjugate. Okay, so this will give me VI into VI's conjugate. VI into VI conjugate will be nothing but all complex quantities. So it is nothing but VI square by ZLI, ZLI conjugate. Okay. So now your complex power at the load PLI plus JQLI is, I can write it as VI square by ZLI conjugate, right? So now little bit, then from this equation I can again write the current expression. So the current expression will become, already we know that PLI minus JQLI is nothing but it is VI star or VI conjugate into ILI at that particular load bus. Okay. So this will give, from this I can write ILI is equal to PLI minus JQLI by VI conjugate. Okay. So then just substituting this VI square by ZLI star, it will become, the expression will become VI by ZLI. No, so this will be ZLI only, not ZLI conjugate. So remove this. This is only ZLI. So your final expression will become VI by ZLI, VI by ZLI, only ZLI. Okay, that's all. So now VI is a complex quantity here, right? So now if I'll write II, that is current injected at a particular bus. So this analysis is for considering only the load, right? Complex load, constant impedance load. Now if I'll find the current injection at that particular bus, then I can write IGI minus ILI, right? Okay, and ILI already I have derived. ILI is VI by ZLI. ZLI, it will be ZLI, not ZLI star. Okay, Vi by ZLi, that is equal to nothing but equal to the current injection, right? So current injection already we derived here, like summation of Yij e to the power j alpha ij into Vj e to the power j theta j, right? Okay. So now just substituting ILI, expression of ILI here, we got this expression. Just substituting, we'll find Vi IGI minus Vi by ZLi, right? So now I can write IGI in terms of other parameters. Just from this equation, I can write IGI as YLI e to the power. If your ZLi is a complex quantity, then I can write, 1 by ZLi, I can write it as YLI, right? So YLI is a complex quantity. It has a magnitude YLI e to the power j of alpha Li. So then substituting this, instead of 1 by ZLi, I can write YLI e to the power j alpha Li Vi into e to the power j theta I, right? Plus other terms. So this is in fact taken to this side and added with this term. Okay, so now we got the expression of the generator current, and it is valid only for the generator buses, and this is from for I equal to 1 to Ng. Okay, now this Ig expression can be embedded to yes, for load buses we can write this expression, right? For load buses, because this Ig I equal to 0, the current from the generator will be 0, so therefore it is 0, and rest of the quantities will be there, right? Now you can see that this if we write this in the matrix form, these quantities, these two equations, if we write in the matrix form, then I can write in this way, right? So this will be up to Ng, Ig1 up to Ng, then other terms will be 0 here. Then this matrix, not exactly it is the Y bus matrix, because when we calculate the Y bus matrix, if you have done load flow studies in your previous courses, this Y bus matrix in fact formed only considering the buses in the system. The number of buses in fact gives the Y bus matrix. Therefore the size of Y bus, if we have n number of buses, the size of Y bus matrix becomes n by n, right? But here it is considering the generator current, and also where is load, the generator currents are becoming 0. Therefore this is a modified Y bus matrix. Therefore it is mentioned Y bus dash, right? So it is considering the generator node directly, not the bus, exactly the bus where the generator is connected. Like you can see here, suppose this is a bus and we have a generator connected to this, right? So during Y bus calculation, we consider up to this, right? Now in this Y bus dash, we are considering up to this point. That means the generator, up to the generator internal EMF we are considering, right? Okay, so now at the IS generator, we can see here it mentions that the IS generator bus, an additional node is created that is marked as I dash with a voltage. Let us say the voltage at that additional node is EI double dash. These are soft transient voltages, so that I can represent with double dash. EI double dash, that is equal to EDI double dash plus EQI JEQI double dash, and obviously it is multiplied with the transformation parameter, that is e to the power j delta I minus pi by 2. So this represents the generator terminal voltage. Okay, this is the generator terminal voltage. The impedance between I dash and II nodes is given as RSI and plus JXDI dash dash, right? Hence Ng numbers of additional nodes are added to the existing n nodes. So we have previously existing n nodes. Now another ng number of nodes which representing the terminal of the generator, right? So that is added to the system, right? So therefore now your size of the Y bus must increase, right? So from this equation we will see how the size of the Y bus will increase. Again it will be reduced, right? So the currents injected at these nodes are given like this. So at these generator nodes, we can write the current injection from the generator as II dash, that is equal to IGI. So that is nothing but is equal to 1 by RSI plus JXT. So if you let us make a diagram, which this is your generator terminal and this is connected with XD double dash and RSI, and this is your bus, VIth bus, right? VI, and this is your I dash node of the generator, right? So therefore here whatever current we are injecting, that is I dash, is equal to IGI, right? I dash, this is I dash node, right? So that is equal to IGI, that is equal to nothing but voltage difference between these two. Here the terminal voltage is EDI double dash plus JEQ double dash, right? So this is also multiplied with e to the power j delta I minus pi by 2. So that will be, so the voltage difference between these two divided by this impedance, right? So that is what mentioned here. And we found that this is the expression, and this will be valid for all the generating buses, and where I dash is nothing but 1 dash to NG dash and I is nothing but 1 to NG. Okay. So now this will in fact give me a large, if we'll incorporate these terms in IG, if I'll add these terms in IG and I will expand this and write in the matrix form, this will give me this equation, right? So that is so one part will be from IG1 to IGNG, and again there will be generator current 0, so it is from 1 to NG, and again from the for the load buses it will be from NG plus 1 to N, right? So therefore it is a very huge matrix, and you can analyze, you can find it easily, right? Not very difficult. So the first part will be E1 to ENG because these are the voltages, right? In fact, this is your terminal voltage, right? E1 is terminal voltage of the generator, E1 to ENG. Then where the generators are not there, for the same generator again, another equation is considering V1 to VNG, right? So these equations, that means from En to Ng, again from 1 to Ng, again from 1 to Ng, E1 ENG and V1 VNG up to VNG. These are for the generators, okay, and generator buses. And this is from VNG plus 1 to VN. This is for load buses, okay. Okay, so now we can say that this is, what will be the size of this bus? Can you bus matrix, Y bus matrix and these vectors, current and voltage vectors, can you tell? So this will be NG, then it is so it will be NG plus N by NG plus N, right? Sorry, this will be NG plus N into 1, this vector, and the Y bus matrix will become NG plus N into NG plus N. Okay. So now the size of the Y bus matrix is increased to NG plus NG times added. That means NG more uh, ng number of columns and rows are added, right? That means your size of the matrix became ng plus n by ng plus n, right? Y-verse matrix. Okay, now these components, each of the component, if we'll see, that is, this is, let us represent it as y2, right? And this is yii and yin. So if I'll represent this, then I can write y bus dash as this, right? Y bus dash is here. This is your y bus dash. This y bus dash is nothing but, this will indicate the previous y bus matrix, right? And these are the added terms, right? So this is y bus dash, y yin. So even y bus dash is not y bus exactly, because we are considering here the current terms. Here we can see y bus dash is here. This y bus dash, we are considering these quantities. So therefore y bus dash is this equation. So this is not in fact equal to y bus, though the size of the y bus dash is n by n, but it is not equal to, the elements are not equal to the y bus matrix, okay? Because we are considering here the generator current here, right? Not the bus current, okay? And in these generator currents, if we'll substitute this, then your y bus matrix will expand, right? So then finally, if we'll write the equation, so this is your current Ig and E dash dash is your terminal voltages and Vn is your voltage at the bus voltages, right? Now if we'll write the final equation, it will be in this form: yin transpose y bus dash having size of ng plus n by ng plus n, that will be multiplied with E double dash Vn. So E double dash is nothing but, this is the terminal voltage of the generator, right? Synchronous generator, and Vn is the bus voltages, where bus voltages of the each bus, right? So therefore the size of this vector is becoming ng plus n by 1. Similarly here the current also becomes ng plus n by 1, right? And obviously Ig, the size of Ig will be ng by 1. This is only for the generator. These are generator currents or generator buses, right? Okay. Now from this equation, I can segregate Vn, and again I'll substitute Vn in Ig, right? So from the second row, from here, I can segregate Vn, right? So if I'll write Vn from the second row, I can write Vn will be equal to y bus dash inverse minus of y bus dash inverse yin t transpose E double dash, right? Okay. So then if I'll substitute this again in the first equation for Ig, I'll substitute the value of Vn, then I can write the generator currents in terms of the terminal voltage E double dash, right? So that is yii minus yin, just this is a reduction, right? So now you can see that now your reduced y bus matrix is this, and this is only in terms of generator current and the generator voltage, right? So this is your generator terminal voltage, this is your generator injected current. So this is your reduced y bus matrix, okay? So now the size of this y bus matrix will be how much? It will be ng by ng, right? So this is also Ig having the size ng by 1 and E dash is ng by 1, okay? So this is the reduced matrix. Now coming to initial condition, we'll talk about this in that, because we'll start means we cannot finish. So we'll talk about this in the next class, how we can find the initial condition and do the analysis again, the stability analysis. Okay, so thank you very much.